Thank you for joining us for this webinar on using the surface energy balance in TEMP-W. My name is Mark LeBeau, and I'm a Research and Development Engineer at GeoStudio. Today's webinar will be approximately 1 hour long. Attendees can ask questions using the chat feature. I will respond to these questions via email as quickly as possible. Finally, a recording of the webinar will be made available so that participants can view the presentation at a later time. The objective of this webinar is to gain insight into how and when the surface energy balance boundary condition should be applied in a thermal analysis. To do so, we're going to focus on the thermal response of a riverbank, and more precisely, the thermal response of a riverbank along the South Saskatchewan River near Saskatoon, Canada. As is often the case, we're going to assume that the geothermal heat flux at the bottom of the domain is equal to 0.06 watt per square meter, or 6 to the power minus 5 kilojoules per second per square meter. As shown on the right-hand side of the slide, the water temperature has been measured at the site and generally increases from near zero in wintertime to approximately 25 degrees Celsius in summertime. Unfortunately, there are no measurements of ground surface temperature or heat flux at or near the site. We therefore have to resolve ourselves to using climate data to determine the prevailing boundary condition. The first type of boundary condition that often comes to mind in such cases is the N factor, which uses the ratio of the ground surface and air freezing thawing indexes to estimate the ground surface temperature. The other type of boundary condition that must also come to mind is a surface energy balance, or SEB. The expression on some of your faces right now is most probably very similar to the puzzled expression on this caribou's face. Luckily, the confusion, and most probably the fear, of the surface energy balance can be resolved by introducing the different heat fluxes at the ground surface. So let's start by introducing these components from left to right. So the first component is the incoming solar radiation flux. We then have the reflected solar radiation flux. Then we move on to the components in red. So the first component is the incoming terrestrial radiation flux. We also have the reflected terrestrial radiation flux. And then we move over to the component in green, which is the sensible heat flux due to the warming or cooling of the air. We also have the component in blue, which is a latent heat flux due to evaporation. And finally, we have the heat flux at the ground surface. The incoming and reflected components of solar and terrestrial radiation can be summed into net radiation fluxes. So we only have one component of solar radiation and one component of terrestrial radiation. All of these fluxes can be grouped into a mathematical equation called the surface energy balance. The terms on the left-hand side of the equation at the top of the slide represent the net radiation flux, a measure of the rate of transfer of energy at the Earth's surface, which can be measured with a net radiometer. In this form, the equation highlights the fact that the net radiation flux warms or cools the air above the ground surface, removes the heat associated with evaporation, and warms or cools the ground profile. The equation can also be recast to isolate the heat flux at the ground surface. This latter equation can be solved by simply taking the ground surface temperature at the last time step, or the initial condition, to compute each of the components on the right-hand side of the equation. Let's now add a degree of complexity by introducing the effect of a snow cover, so the white arrow on the right-hand side of the slide. For simplicity, we assume that the heat flux through the snow cover is equal to the heat flux at the ground surface. In other words, we assume that the snow has no capacity to store energy. If we now move all of the terms over to the right-hand side of the equation, we can determine the temperature at the surface of the snow cover using our root finding technique. This temperature and the inputted thermal conductivity of the snow can then be used to compute the temperature at the ground surface using Fourier's law. Now that we've defined the surface energy balance and provided methods of solution in cases with and without snow cover, we're ready to move on to the input requirements. The selection of one of these three options depends on the availability and type of radiation data. The first option applies to studies in which net radiation data is available. The second option applies to studies in which incoming solar radiation data is available, and the last option applies to studies in remote areas where there are no measurements of net radiation or incoming solar radiation. Other inputs include air temperature, wind speed, vegetation height, which is optional, actual evaporation, snow depth, and snow thermal conductivity. Note that options 2 and 3, which are based on measured or estimated solar radiation, also require albedo and relative humidity, which is also optional. The case study considered in this webinar is located near a weather station that provides incoming solar radiation data. We will therefore choose option 2 for now and collect all relevant data. So we've collected all the data, but one question remains to be answered. How will the incoming solar radiation data be converted into net radiation data? To answer this question, let's walk through the computations for a specific day, say July 1st, at which time the initial ground surface temperature is 18 degrees Celsius, the air temperature is 9 degrees Celsius, wind speed is 2 meters per second, and actual evaporation is 1 millimeter per day. The first step in the process consists in computing the net solar radiation flux as the product of 1 minus albedo times the incoming solar radiation flux. The second step consists in computing the net terrestrial radiation as the difference between the outgoing and incoming terrestrial radiation. The outgoing radiation is equal to the product of surface emissivity, the Stefan-Boltzmann constant, and the fourth power of the temperature at the ground surface. The incoming radiation is equal to the product of air emissivity, the Stefan-Boltzmann constant, and the fourth power of the air temperature. The third step consists in computing the sensible heat at the ground surface as a product of a convective heat transfer coefficient and the difference between ground and air temperatures. The convective heat transfer coefficient is equal to the volumetric heat capacity of air divided by the aerodynamic resistance to water vapor flow or heat flow from the soil surface to the atmosphere. The fourth step consists in computing the latent heat flux due to evaporation as the product of actual evaporation, the density of water, and the specific latent heat of vaporization. The fifth and final step consists in computing the flux at the ground surface as the difference between net radiation and the sum of sensible and latent fluxes. Now that our understanding is complete, we can go ahead and apply the boundary condition in an analysis. Although surface energy balance boundary conditions can be applied in both one-dimensional and two-dimensional analyses, we strongly recommend that they mostly be used in one-dimensional analyses and that the computed ground surface temperatures be used as boundary conditions in multi-dimensional analyses. This recommendation is based on the fact that surface energy balance boundary conditions are computationally intensive and require very small time steps and fine meshes. The first analysis, in this case, will be set up using daily climate data. So let's go ahead and open the file named Surface Energy Balance Measured Solar Radiation. Okay, so let's go ahead and set up our first analysis. And when I set up an analysis, I like to follow a numerical modeling methodology that we've established. And the first step in this numerical modeling methodology consists in defining the geometry and the geology. So in this case, the geometry is relatively simple. We have a 30-meter high column of soil. And the geology is also relatively simple. We have 28 meters of saturated soil at the bottom of the soil column and 2 meters of unsaturated soil at the top. So once we've defined the geometry and the geology, we're ready to move on to the next step of the numerical modeling methodology, which consists in defining the partial differential equation as well as the constitutive models that describe the material properties. So let's go ahead and do that. So we're going to go into Define Projects, and we're going to zoom over here to the analysis type. And we see that the analysis type has been set equal to steady state. This implies that the partial differential equation is equal to 0 on the right-hand side. In other words, the heat going into the soil column is equal to the heat going out of the soil column because there is no change in energy within the column itself. So this is exactly what we want under steady state conditions. The next thing that we want to do is to define the constitutive models that describe the material properties. So we're going to go ahead and do that. Draw materials. So we get these empty dialog boxes, but we're not afraid. We simply click on Define, and now we add a new material. So the first material that we're going to go add is soil under saturated conditions. And we're going to give it a nice bright orange color. The next step consists in defining the material model. In the case of material models, we have a choice between full thermal, coupled convective thermal, and simplified thermal. As its name implies, convective thermal models apply to convective heat transfer, where we have groundwater flow that moves into our domain and that is changing the volumetric water content and therefore changing the thermal properties. This is not the case in our analysis. In our analysis, the volumetric water content remains constant. We're therefore going to use either a simplified thermal or a full thermal material model. In the case of a simplified thermal material model, the water in the soil freezes at a given temperature. In the case of a full thermal material model, the water will freeze over a temperature range. So this is exactly what occurs in a silt. So we're going to select that full thermal material model. And by doing so, we have to define a number of properties. So we have to define the thermal conductivity function, the unfrozen volumetric water content function, the volumetric heat capacity under unfrozen and frozen conditions, as well as the in situ volumetric water content. So let's go ahead and define the volumetric heat capacity. So in this case, the volumetric heat capacity under unfrozen conditions of the saturated soil is equal to 1,952. And under frozen conditions, 1,165. The in situ volumetric water content is equal to the porosity, so 0.35 for our silt. And then we move over to the thermal conductivity function. So clicking on the ellipsis, and we see that we've already defined thermal conductivity functions for our materials. So we have the saturated soil, and as we see here, the thermal conductivity increases as the temperature decreases, which is very logical, right? The thermal conductivity of water is lower than the thermal conductivity of ice. If we change the temperature range over to -10 here, well, we see that the thermal conductivity remains constant at lower temperatures. If we increase the temperature range, we see that the thermal conductivity also remains constant in the unfrozen region. So it is ascribed to the point, so that first point applies to the conditions at positive temperatures. So we're going to select that correct function and apply it to our material. And now let's move on to the normalized unfrozen volumetric water content function. So in the case of the saturated soil, we see that the normalized unfrozen volumetric water content changes from 1 down to approximately 0.05. Essentially, we're normalizing with respect to porosity. Or in this case, because it's saturated soil. So we're going to essentially ascribe it to our material, and we're going to add a new material and call that soil under unsaturated conditions. And we're going to give it a nice light orange color. And once again, we're going to use the full thermal material model to describe the behavior of the material. So the volumetric heat capacity under unfrozen conditions of the unfrozen soil, 1,534. Under frozen conditions, 1,014. In situ volumetric water content, 0.25, which corresponds to degree saturation of approximately 70%. And we're going to simply select the correct functions and ascribe them to material. So soil unsaturated and soil unsaturated. We can close that dialog box down, and now we're ready to ascribe the material to correct portions of the domain. So the unsaturated soil goes at the top of the soil column, and the saturated soil at the bottom of the soil column. Once we've done that, we're ready to move on and define the boundary conditions, which is the third step in our numerical modeling methodology. Let's go ahead and do that by going into the Draw Boundary Conditions dialog box. Once again, dialog boxes are empty, but we simply click on Define and Add New Thermal Conductivity Functions, and we're going to be defining, boundary conditions, and we're going to be defining boundary conditions at the bottom at the top of our soil column. So the boundary condition at the bottom will be a geothermal heat flux, and the geothermal heat flux, which is a heat flux boundary condition, will be set equal to 6 to the power minus 5 kilojoules per second per square meter. And we're going to set the color of that boundary condition over to a nice burgundy. And we're also going to add a boundary condition for the ground surface. So that will be the initial ground surface temperature. So let me correct that right here. Initial ground surface temperature, which will be essentially a temperature type boundary condition. So temperature, which is set equal to 3 degrees Celsius. We're going to change the color of the boundary condition over to a nice bright green. Close that down. And now we have to ascribe the boundary condition. And we can either ascribe it to lines or points. In this case, we want to ascribe it to points. So we're going to ascribe the initial ground surface temperature to the top of the column and the geothermal heat flux to the bottom of our column. Although we're ready to move on to the next step, we realize that we're going to be using a surface energy balance boundary condition. This will require fine meshing in the upper portions of the column. So we're going to address this by adding points. So we'll draw points. And we're going to draw points at the top, so at 29.8 meters. And I'm going to draw points as well as we go down the column, so at 25, 25, and 10 meters. And I'm going to close that down, and I'm going to refine the mesh into different portions. So we'll draw mesh properties, and I'm going to click on the different portions of the domain, and I'm going to change the length of the mesh, or the distance between the points, to specific values. So in the lower portion, I'm going to use very large distances, and I'm going to decrease this distance as I approach the ground surface. So 5, 1, and then I'm going to decrease that to 0.5, and then 0.1, and 0.05, and 0.025. So as you can see here, I'm using very fine mesh, very small distance between the points. And in the upper portion, I'm going to use 0.005. This will be, I'm using these very small meshes in order to account for the large thermal gradients that will occur at the ground surface due to the large variations in flux at the ground surface. So once I've done that, I'm essentially ready to move on to the fourth step of the numerical modeling methodology, which consists in solving the problem subject to the boundary conditions. In other words, clicking on the Start button. So we click on the Start button, and the software does its magic, and it solves the analysis for us. Once that's done, we move on to the fifth step, which is the most important step of the numerical modeling methodology. In essence, we have to interpret our results and apply our engineering judgment. So we go into Draw Graph, and I can't insist on this point enough. Always draw graphs of your results. So we're going to add a new graph, and we're going to call that 6 temperature profile. And what's the temperature profile? Is temperature as a function of y. We're going to set the location, and the location will be all the nodes of the soil column. We're going to show the graph. Now the graph looks quite funny because we have y on the x-axis. So we much rather rotate that graph 90 degrees and express y on the y-axis and temperature on the x-axis. So we see that we have a bilinear relationship between temperature and elevation, which is quite normal because we have different thermal conductivities in the saturated and the unsaturated portions of our column. So we can close that down, and we've essentially correctly modeled our initial conditions. So let's now go on to the heart of things, and we're going to add a surface energy balance boundary condition to the top of the column and run another analysis. So we're going to go into the definition view, and we're going to go add an analysis to the existing analysis. And this will be a transient analysis. And we're going to rename that analysis SEB daily for daily climate data. And we're going to call it spin up. So essentially, we're going to, not sin up, but spin up. Essentially, we're going to erase the initial conditions by running our numerical model for a very significant amount of time. So we're going to define the time right here. And the time that we're going to use is 3,650 days. That's right, we're going to run it for 10 years. So 10 years, and what we're going to do is we're going to use 21,900 steps. which corresponds to 4-hour time steps, which is the recommended time step in this type of analysis when we have temperature data which will vary on a daily basis. And what we want to do is save every 2190 step. In other words, save every year. So we close that down, and now what we're going to do is we're going to define the boundary condition at the top of the soil column. So draw boundary conditions, and what we want to do is we want to apply a surface energy balance boundary condition. So we're going to go ahead and click on define, and we're going to add a new boundary condition, and that will be called SEB daily data. So what is the surface energy balance boundary condition? Well, it's down here. So we're going to select that boundary condition, and by doing so, we see that we have a number of inputs that we have to enter. These are the inputs that we talked about in the presentation. In essence, instead of going directly into these dialog boxes, we can close this down and import a data set in which all of that data exists. So we close that down, close the dialog box down, and we go into define data sets. And we've already set up the data sets. So we've looked through the climate data, and we've created these CSV files. So data climate for YXE, which is Saskatoon, and we open it. So we see that we have a time header, which describes time, and as you notice here, time of start is 0. So we have data for every day of the year entered directly in this CSV file. We have data for air temperature, relative humidity, wind speed, snow depth, solar radiation flux, and evaporation. So let's go ahead and import that data directly into our data set. Sorry. So once we've done that, we move on to redefining our boundary condition. So go into draw boundary conditions, define, and let's go back to our surface energy balance boundary condition. And we're essentially going to change the color of that boundary condition over here to a light orange. First field is to define the evaporation data. In this case, the evaporation data will not come from a water transfer analysis, but it will be a user-defined evaporation data. We're going to click on the ellipsis and add a new function. We're going to call this YXE, evaporation, and we're going to add a suffix which will be daily to describe the data. So this data will be a step data point function, and we're essentially selecting the data set. So automatically populates that field. And we want to cycle this function over 365 days. So at every 365 days, we'll be repeating the function. So we close that down. Don't forget to ascribe it to our boundary condition. We move over to the air temperature, and we essentially create a new function called this YXE dash air temperature. Air temperature. So air temperature, a step data function, climate, and there we have air temperature. We're going to cycle it once again over 365 days. We close that down. We don't forget to ascribe it to our boundary condition. Move over to wind speed now. We add a new, so that would be YXE dash wind speed. Whoops, sorry, I zoomed in here. YXE dash wind speed, and I'm going to add a suffix daily, and that will be step data point function YXE, and we automatically import the wind speed. So that will be cycled on a 365 day basis. and I realize that I did not add the suffix to my air temperature function, and I'm going to do that right now. So I'm going to click back on the ellipsis. I'm going to change the name or add a description to the name, daily. So what type of radiation data do we have? Well, we don't have net radiation data, we have solar radiation data. So in this case, we're going to enter the solar radiation flux. So we're going to add a new function, and that will be YXE solar radiation flux. So what type of boundary condition is that? A step function once again, and it'll be from the data set that we have, and we're going to cycle it over 365 days. So close that down, ascribe it to our boundary condition, and now we move over to albedo. So albedo, we're going to create a new function. We're going to call that albedo, and this is quite simple. What we're going to do is we're essentially going to have a albedo corresponding to snow so that would be 0 the first time, and 0.8 for snow during winter time. At 91 days, when we change from negative temperatures over to positive temperatures and the snow disappears, we'll apply 0.23. We'll move over to 298 days and we'll apply 0.8. And we'll essentially cycle that function over a 365-day period. So we see that we have snow, grass, snow, grass, snow, grass, snow, grass. So we close that down and we ascribe it to our boundary condition. Move over to the next field, add, keep on going to the import, but don't have to import. So YXE, and this is relative humidity, and it's daily data. So relative humidity under daily data, I want to use a step data point function, and there we go. We import that function and we cycle it over a 365-day period. We close that down and ascribe it to our boundary condition. Move over to the snow, user defined, snow in this case. So I'm going to define the thermal conductivity first of all. So thermal conductivity of our snow is set equal to just a sec here so that I can find the value. Yeah, there we go. 1.20949 to the power minus 4 kilojoules per second per meter per degree Celsius. And we essentially select the snow data from our function, so from our data set, YXE snow depth, and that will be daily data. In fact, snow depth is always daily data. Step data function, import the climate function, and cycle that over 365 days. So we close that down and ascribe it to our boundary condition, move over to vegetation. In this case, although we don't have vegetation, I'm just going to define a bare ground condition. So new, and I'm going to call this bare ground, and we're essentially going to use a step function of 0, and we're not going to cycle it because it will be 0 throughout. So if we review our boundary condition, we have vegetation, which is bare ground, snow data, which comes from the snow depth, and it's daily data. We have relative humidity, which is daily. Oh, once again, I forgot the suffix here, so I'm going to add it. So Y, and that's daily. And I'm doing this because later on, we'll be adding hourly data. So close that down, wind speed data, air temperature, daily, and YXE. So there we go. We've defined our surface energy balance boundary condition. Not very hard when you have access to data sets. So we close that down, move over to the node or the point at the top of our domain, and describe the boundary condition. And while we're at it, we're going to add another analysis, which will be the analysis that we'll be looking at. So we spin the analysis for 10 years, and then we're going to be looking at the last year, or the 11th year, as our model results. So we go into the define project, and we're essentially going to add a new temp analysis. Temp analysis will be SEB daily. So that will not be our spin up analysis. And I'm going to close that, and I'm going to essentially, I could have done this differently. Yeah. So we're going to define the time steps here. So that will be over 365 days. And what we want to do is run that for every 4 hours. So that would be 2,190. Yes. And we want to save every day. So we want to have all those results and be able to interpret those results later on. So we close that down, and as you can see, the surface boundary condition is applied to the analysis. As a good rule of practice, I'm going to unselect the analysis that I've already solved, and essentially going to solve the analysis by clicking on the Start button. Okay, so the analysis is essentially solved, but in this case it took a significant amount of time. In fact, I was running it on my laptop and it took approximately 1 hour. So we weren't going to wait for 1 hour. So I essentially extracted the data and created this graph. So by the magic of video editing, we're here with all the data in hand. So we now have the temperature at the ground surface of the riverbank. Although we could potentially go ahead and apply it to the ground surface in a multi-dimensional analysis, I think it wise to go back and rerun the analysis with hourly climate data. So what we're going to do is we're going to go back in our file and set up a new analysis with, in this case, hourly data. Okay, so we're back in our analysis and we see that the analyses have been solved. So what we're going to do is we're going to add a new analysis, in fact, 2 new analyses for the SEB with hourly data. So we're going to go to the initial condition analysis and we're going to add a TEMP transient analysis. And we're going to rename that analysis SEB hourly, and we're going to add spin up because this will be the 10-year spin up analysis. And we're going to go ahead and define that analysis. So the time, in this case, we want to run it for 3,650 days or 10 years. We want to, in this case, given that we have hourly data, capture those hourly data and therefore set the time step equal to 1 hour. So 1 hour for 10 years is 87,600 time steps. And we want to save that at every 8,760 time step or at every year. So we close that down and now we're ready to create the boundary condition. But as we know, we have to import a data set. So we're going to do that right now. Go into Define Data Sets. So we have the data set for daily data, and we're going to add a new data set for hourly data. So simply clicking on Open, we get the different fields. So we have air temperature, relative humidity, wind speed, solar radiation, and evaporation. So we simply click on Import, and the software does its magic, and it imports all that hourly data. So we can close that down and now create the boundary condition. go into Draw Boundary Condition. As you can see, those data sets are fantastic. They decrease the time of creating such boundary conditions for sure. So we're going to create a new boundary condition. It will be an SEB on an hourly or with hourly data. So what type of boundary condition do we want to create? It's a surface energy boundary condition. We click on surface energy. Surface energy balance, yes. So what user define evaporation. In this case, we want to define a new function. So we don't want to use the daily data. We want to use or create yx, whoops, keep on doing that, yxe dash, and this is evaporation on an hourly basis. I'm quite neurotic, so I'm going to add capital H here. So step data point function, and we're going to add the hourly data, and we're going to cycle that over a 365-day period. If I move over to the daily, we see that we have much more resolution in the data on an hourly basis. Don't forget to ascribe that hourly function. Move over to the air temperature, add a new. So that will be yxe dash air temperature, and it is hourly data. So just trying to be clear so that we don't get lost when we're looking into our files. So step data point function and then hourly, and we want to cycle that on a 365-day period. So if we have a look at the function, much more resolution there, and a change in the range or the maximum of the air temperature and the minimum of the temperatures as well. Close that down, ascribe it to the boundary condition, click on wind speed, create a new one. So that would be yxe, and that's wind speed on an hourly basis. And we want a step data point function, so that would be hourly cycle 365. Close that down, describe it. So that's wind speed hourly. What type of radiation? It's solar radiation that we have. So we're going to add a new one. So that's yxe. Solar radiation, and essentially that would be a step function, solar radiation on an hourly basis. We're going to cycle that function over a 365-day period. Now we see much more resolution in the data. So, didn't write hourly, so I'm going to edit that, right? Hourly, just for clarity. Close that down. Use the same albedo as we had before. Relative humidity, we have data. So that would be on an hourly basis. That's a step data point function on an hourly basis. And the period is 365 days. Close that down. Move over to the relative humidity. And now we can import snow data, but snow data is always on a daily basis, so it's not provided on a hourly basis. Thermal conductivity, 1.20949 to the power minus 4. And then vegetation, well, we'll be using the same bare ground function. So we have bare ground, snow on a daily basis, because there are no hourly basis data. Hourly basis for relative humidity. Hourly basis for solar radiation. wind speed, temperature, evaporation. So let's change the color just for clarity right there. Close that down, and we can ascribe it to the top of our soil column like so. And then what we're going to do, we're going to close that down, and we're going to essentially add another analysis, a TEMP-W analysis, and call this SEB, and that would be hourly. And we're going to define that project by defining the time stepping scheme. So it'll be a 365-day duration analysis. We want hourly time steps, so that would be 8,760 time steps. And we want to save them at every time step because we want all of the results in order to interpret what's happening in the software. So we close that down, and we see that the boundary condition has automatically been taken from its parent. So let's go ahead and click only on the analyses that are not solved. If you click on an analysis that's already been solved, the first thing that the software does is it erases that data. So goodbye, and you have to rerun the whole thing again. So we're ready to run these analyses. So let's click on Start. Now that we've extracted the data, we can compare the results to those found with the daily climate dataset. As expected, the results with hourly climate data shows greater variations in temperature. These variations are most significant during summertime when solar radiation flux is greatest. The variations also seem to be skewed upwards with respect to that found with the daily climate dataset. Although some skewness is expected, the displayed results seem to indicate that the hourly dataset leads to higher daily averages than that found with the daily dataset. A look at the surface heat flux reveals that heat extraction, the negative values, are most significant during spring, around day 91, and fall, around day 298. Further insight into the effect of the different datasets can be gained by computing and plotting daily averages of both temperature and heat flux. The plot of the average surface temperature confirms that the hourly climate dataset leads to higher daily averages. A close inspection of the data reveals that the hourly climate dataset produces a 2.1 degrees Celsius increase in average annual ground surface temperature and a 4.2 degrees Celsius increase in maximum annual ground surface temperature. If you're slightly curious, you're asking yourself why that happened, right? Shouldn't the hourly data set simply lead to daily variations with the same average as that found with the daily climate data set? The answer to this question can be found in the variations of incoming solar radiation flux and air temperature on a given summer day. As expected, the air temperature evolves in a sinusoidal manner and reaches a maximum at time 102.7, which corresponds to approximately 5 p.m. The solar radiation flux, on the other hand, follows a half-sine function with a maximum at 102.6, which corresponds to 2 p.m. The near coincidence of these maximums leads to significant net radiation in early afternoon. The equation on the right-hand side of the slide highlights the contributions of both incoming solar radiation and air temperature on net radiation. This combined effect cannot be captured or modeled using daily solar radiation fluxes and air temperatures. It is thus strongly recommended that hourly climate datasets be used with the surface energy balance boundary condition. It must be noted that the dataset functionality makes it very easy to use any dataset, be it daily or hourly. So we've established the importance of hourly changes in incoming solar radiation and air temperature on the numerical results. Some of you may now be thinking of your projects and realizing that you don't have access to radiation data. In this case, you can use the estimation routine provided in the software. In other words, you can use option 3. So how does the estimation routine fare against a dataset approach? Well, before answering that question, we have to review how the solar radiation flux is estimated. Let's once again walk through the computations for a specific day. Once again, taking July 1st. The only additional input that we need is latitude. The first step in this process is to compute the incoming extraterrestrial radiation flux using the equation shown at the bottom of the slide. The parameters in this equation are the solar constant, G subscript SC, the inverse relative distance Earth-Sun, D subscript R, the sunset hour angle, omega subscript S, the latitude, phi, and the solar declination, delta. The second and last step in the process consists in computing the incoming solar radiation using Angstrom's formula. This formula accounts, or at least it attempts to account, for cloud cover. This is no easy task, considering that 75% of extraterrestrial radiation reaches the Earth's surface on a sunny day, and that the percentage can decrease to 25% on a cloudy day. The equation includes two empirical constants, A subscript S and B subscript S, the actual duration of sun, N, the maximum possible duration of sunshine, capital N, and the extraterrestrial radiation, Q subscript A. So let's go ahead and open a new file. In this case, we'll be opening the file Surface Energy Balance, and we'll be setting up an estimated solar radiation. So we're going to be using option 3. Okay. So we're in the analysis in which we're going to be estimating the solar radiation flux with the functionality provided in the software. So in this particular analysis, everything's already set up, the data sets have been imported, and the analyses are set with the correct time steps. So what we're going to do is simply define the boundary condition. So go into Draw, Boundary Condition, Define, and we're going to add a new thermal boundary condition. We're going to call that SEB, estimated solar radiation flux on an hourly basis. So once again, a surface energy balance boundary condition, evaporation flux is user defined based on the hourly data, air temperature is hourly data, wind speed, hourly data, solar radiation, we're not going to define that right now. We're going to define it right afterwards. Albedo, hourly, snow data. Snow data, as we said before, is mostly on a daily basis. And the thermal conductivity of the snow, 949 to the power minus 4 kilojoules per second per meter degrees C. And the vegetation is on the bare ground. So let's go ahead and look at the functions available for solar radiation. So we already have the functions based on the daily and the hourly data, but in this case we don't have any data. So we're going to click on the ellipsis and we're going to create a new function. So we're going to call this YXE, estimated solar radiation flux on an hourly basis. So what are we going to do? We're going to simply select the estimated solar radiation option from the drop-down menu, and we're going to set the latitude to 52.2. So the latitude in Saskatoon. And we want to distribute this solar radiation over each day. So by doing so, we see that there are a number of sine functions, so we could look at those by essentially zooming in. Say that we zoom in at 182 on day 182, well, we see the function on day 182. So we can close that down, and we must not forget to ascribe it to the boundary condition. So ascribe it to the boundary condition in this case, y-axis estimated. So hourly, 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 and then snow data. So everything seems to be defined correctly. And we could change the color, put that a bright red like so, close that down, and then ascribe it to the boundary condition in both analyses like so, and close that down, and we could start and solve the analyses. Now that we've run the analysis and extracted the data, we can compare the results to those found when using measured incoming solar radiation. In this case, the surface temperatures compare fairly well. Although the variations are similar, there seems to be a slight upward skew of the lower limit of the variations during summertime. Right here, in this region right there. The plot of the average surface temperature confirms that the estimated solar radiation leads to higher daily averages. A close inspection of the data reveals that the estimated solar radiation dataset produces a 2.1 increase in average annual ground surface temperature and a 0.3 degrees Celsius increase in maximum annual ground surface temperature. This difference is somewhat anticipated and most likely due to the difficulty in estimating cloud cover. This latter affirmation is confirmed when comparing the measured and estimated solar radiation on a given summer day, where a cloud cover most likely impedes the solar radiation from reaching the ground surface in the early portions of the day. Right over here. It can therefore be concluded that the ground surface temperature of the one-dimensional analysis with hourly climate dataset and measured incoming solar radiation can be used in a multidimensional analysis of the South Saskatchewan riverbank. Unfortunately, we've reached the time deadline for this webinar, but I'm going to leave you with a video that shows the setup of this analysis as well as the solution in our new product, TEMP 3D. Thank you for attending this webinar, and please don't hesitate to reach out if you have any questions. The video that I just mentioned will follow.